So let's get it started. Can you see? I guess it's good enough. So my name is Saewung Kim. I'm an assistant professor in Department of the Earth System Science. And then just let me briefly introduce myself. I'm a second year out here. And I grew up and then went to actually college in Korea. And then I got Ph.D. in Atlanta at Georgia Tech. And then after that, I spent 4.5 years in a national lab called National Center for Atmospheric Research, doing some research out in Boulder, Colorado. And then I started a faculty position out here last September. So English is not my first language, so there might be little difficulties in terms of language barrier, things like that, but I will try to do my best. And what else? And then there's open courseware. It's recording this lecture, and then it will be uploaded on YouTube. But usually viewing number is less than 100, so you don't need to worry about anything. And maybe it can be used for your future review before the exam, things like that. I guess it can be a good use for you. And then this is university policy, also I think state of California policy that moving towards to the this kind of open courseware and then online education, things like that. So this is kind of big trend, so we cannot avoid. So please understand that. So if you are not that big fan of filming on YouTube, things like that, let us know. If you have any concerns about filming the class, let us know. But I bet you will be just fine about it. And then if you or face on the, I think video, I think there will be some written consent form, things like that will be out there. We need to get signed from you, things like that, so your privacy will be kept, all right? But however, if you have any concerns or questions about filming, just let me know. And my office hour is Tuesday and Thursday, 2 hours before the class, 1 p.m. to 3 p.m. Probably you can see my office information and my telephone number on the website. I'm on the crowd hall. So crowd hall is like that side. So if you are not familiar with the physical science campus, so this is Aldrich Park, and then we are right here. And this is a lecture hall right here. And then there's one kind of big building called Lowland Hall, which is mostly occupied by the chemistry department. And then out here, the building called Lines Hall, which is mostly occupied by physics and mathematics. And then our Earth System Science, relatively small building, but relatively newly looking building called Crowd Hall is right here. So my office is third floor of this building. So if you have any questions or concerns about this class, just come see me during the office hour. Or you can just, if this time slot is not a good time for you, you can just email me to make a separate appointment. So probably you all know about it. This is general education class. So gearing towards non-science major students. Just I look through the, most of you guys major, it seems like most all of you are not science major. So it's not gonna be that much scientific, but it's gonna be a little bit scientific, all right? So it is listed in 3 different categories of the general education. So obviously one thing is science and technology. And then the other thing is nice fancy words, but it's about mathematics, the numeric skill that you need to have as a college graduate. And then the other thing is that maybe it is not quite, you don't quite get it why air pollution issue can be an international or global issues. But air pollutants is not really staying right there in the city. Now we know that air pollutants and then all those greenhouse gases, if you think that is also air pollutants also, it's not staying there, actually it is transported here and there. So it becomes the international issue, also diplomatic issues, some countries, so it can be seen as international and global issues. So it is listed in 3 different categories. So in terms of science, I guess I should warn you a little bit. So we will talk about a little bit about physics and chemistry. I can see the little bit worried face. But it's not going to be that deep. And then if you have any problem in understanding things like that, so come see me or come see the TA. We will just work hard until you can understand everything, right? So it's not going to be that difficult. Maybe at first it can be difficult, but if you just try to read and then try to understand again and again and again, eventually you will understand, I hope, everything, or most of the thing, or at least some part that you can pass this course. So don't worry about it. And then there will be a little bit of the math skill. It's mostly arithmetics. And then the table reading skills, and then chart reading skills. That's what I'm going to impose during this class. Again, it's not going to be super difficult, so don't worry about it. And then we will finally discuss about some of the economical or societal consequences of air pollution during the course. So we'll discuss about some air pollution problem, like photochemical smog, or aerosol problem, particle pollution issue, things like that. And then we will discuss about what is the science context behind of that air pollution problems. And then we will try to understand those problems quantitatively using the numbers and units. And then finally, we will discuss about those air pollution issues in context of the societal impacts. All right? So that's the whole scope of this course. And then this is kind of my expectation that after you successfully pass this class, I hope you can achieve this kind of goals. First thing is that there's a lot of, you can come in. So there's a lot of news coverage these days dealing with environmental problem, not only in this country, but also other countries' problem, because these days every country is connected, and then probably you have a chance to travel all around the world near future. So I hope after this class you can understand. So it's not by just hoping for. So my goal is I just want you to understand some of the scientific coverage about environment on the major news media. So how many of you actually reading newspapers and then watching TV news, things like that? Maybe 10%, 15, 20. So maybe this is a good starting point. You can just start to read the newspaper, things like that, and then to learn what's going on out in the world, all right? And then the other thing is that you can probably, I can see there are many people actually talk about some issues, right? So air pollution is a big issue, climate change is a big issue, things like that. But not many people actually say the problem with the numbers, right? So for example, for that air pollution issue, then so what's the real problem of the air pollution? How many people are actually dying due to the air pollution issues, or economically, so what's the money amount that we lost due to those kind of problems? So I hope you can understand some quantitative understanding on those kind of air pollution issues after this class. And then I will talk about a lot. So basically, if you review that textbook, so that textbook is written by a scientist. So of course, obviously, it contains a lot of scientific jargons in it. So I want you to have the basic understanding what scientists are using in terms of the some jargons, and then sometimes the usage of words that normal conversation and scientific conversation can be a little different. So I hope you can understand the uses of the scientific jargons and then the words. And we'll talk about basic mathematical skills. And then we will read a lot of tables and then graphs to understand the air pollution problem. So after that, even these days, so we scientists not really big fan of using the writing words and then writing big text, things like that. We just try to convey the information using the table or the chart. So I will try to educate you guys to how to read a chart and then how you can get information out of the table or chart during this quarter, so that you can have skills related with reading graphs and charts. And then finally, it's about some societal implications of the air pollution. So this is the textbook. Maybe we should turn the light down a little bit. Where's the switch for the light? Okay, Ian, can you see the switch back there that we can just turn off the front part of the classroom? Nope.
It should be on the podium.
Oh, yeah?
Yeah. No. It's like
on your left-hand side.
Oh. So that's June. Here you go. So this is much better. So this is textbook. How many of you actually bought the book? Yeah, some of you. So I reserved this book in the library. So if you need, you can just go read the book that reserved in the library. And then this is a really good reading. There's a lot of photos in it, and then it's kind of entertaining to read. But some part of the description of this book is very technical. But we are not really going to touch the technical parts of this textbook. So I will use this book as a guidance of topics that I will introduce to you guys. And then as a reading assignment, I will just assign some chapters of this book as a reading assignment. But my point is that this is good read. And then depending on your background, it can be very easy reading, or it can be very difficult reading too in some part. But in general, I think most of you guys can understand what's going on in this book pretty well. So don't need to worry about you cannot understand every single point of this book. So no need to worry about it. So this is just guidance of the learning for this whole quarter. So I will use textbook as for that use. All right. So this is the information of the reservation for this book. I think in the library just only one book is reserved, so it might be very competitive, but you know, that's the life, I guess. So iClicker instructions. So the attendance will be checked by iClicker. So which is looking like this, and then I just activated this thing right here, and then you need to set the right frequency for this thing. And then my understanding is that the base frequency in this classroom is CC. So everybody knows how to set the frequency, right? Set the frequency CC. So if you just push this on and off thing, then it will be blinking. And then what you gotta do is that push CC. So that's how you set the frequency.
Is that iClicker 1 or iClicker 2?
So I can go either way. So I'm not gonna ask any question require more than iClicker 1. So you can use both. So you can get the full point with 2 absences or less. So you can free to skip 2 classes, which means that to get the full points for the points assigned for the attendance. So this is evaluation. So participation is 4%. And then homework, there will be 4 homework sets will be given during the this course of quarter. And then that's going to be 20%, and then 5% each for the homework set. And then quizzes. And then there will be weekly quiz every week from next week. I will assign quiz Friday, 5 p.m. And then on the triple E. and then it will be closed Wednesday after that, week after that. Yeah, so 4 days after, 5 days after that, the quiz assigned. So there will be 10 quiz sets, but I will count only 7, right? So if you can get the full points for the 7 quiz set, you will be fine. So it's going to be 14%. So there will be midterm, and then final, and then point assigned is that, and then just, typical thing that to get A, got to be 90% or more, B 80%, and C and 70%. So this is iClicker thing. And then another thing that I need to tell you is that just like that first lecture note, every lecture note will be uploaded on the Dropbox 5 p.m. the day before the class. So next Tuesday lecture note will be uploaded by Monday 5 p.m. All right? So that's going to be the routine. And then homework set. And then one thing I need to note too is that there's a late submission will be a reduction of 30% per day. So 3 days after, there's no need to submit the homework, right? So I'm not just trying to be mean about this thing, but rather just, kind of this society is all just learning by the deadline. So I think in school, you need to learn to keep the deadline. So if you think you have difficulties in keeping deadline, please let us know beforehand that the deadline of this homework assignment. The quiz will be on the EEE. As I said, there will be 10 quiz sets, but only 7 best scores will be counted. So although you missed some quiz set because of your personal issue, there are 3 chances you can just pass by. So there will not be any makeup quiz for the quiz part. All right? And then exam. I teach this class actually this winter quarter, so it's February and March. I will let you know the new dates about it. So it's going to be closed book, and then only a non-programmable calculator will be allowed. And then there's some policy about the backup exam, so please read through it. And then this is this winter quarter's student grade distribution. I expect probably about the same percentage of A, B, and C, and D. And there was about 6 students was sign up, pass and fail. Then one kind of funny episode was that after the quarter, a student signed up the pass and fail, emailed me that, did I pass? And then actually I just looked through the older scores. And then if she signed up this class as a letter grade, she got an A, but she signed up the pass and fail, so I just gave her a pass. So if you signed up the pass and fail, so about the middle of the quarter, you gotta take a look at scores you got, and then if you want to change it, you gotta change it. So this is, I think, updated schedule. So the midterm is gonna be October 29th. So in some region, if you cannot attend October 29th, please let me know beforehand, all right? So final, let's hide it. Where is it? It's gonna be December 10th. So that's the exact date that was on the course schedule. So I don't see any problem for this December 10th date. But if you have any problem with this October 29th date, please let me know beforehand. So TA, there is going to be a discussion session on Monday and Wednesday. There's a TA back there, Ian Rangam. You can stand up and say hello to everybody.
Yeah, hi, my name is Ian Rangam. I'm from Boston. I'm TAing Mondays and Wednesdays, and we have office hours preceding the discussion sections.
Yep, so he's, yep.
Yeah, that's all.
That's all? Yep, yep.
If you have any questions, I'd be more than happy to help.
So I think, is this your right email address? This one right here?
Yeah, that's it.
So the email address one on the course syllabus, I somehow just made some typo. So this is the right email address for Ian. And this is the discussion session schedule. Now it's going to be Roland Hall, which is chemistry building right here. And then he will discuss mostly about class material, and then quiz question and homework. So this is basically our policy about the homework and quiz. Is that if you approach us and then ask about quiz and the homework question, we will let you know all the way until just before the answer, so that you can get the full points of the homework and quiz if you are passionate about this class. All right? So if you are really interested in getting reasonable grade, then there's a way to get there. It's not that difficult to do. So it'll be a good use of the 1 hour, right? So his office hour is going to be 2 p.m. to 4 p.m. on Monday, and then 11 a.m. to 1 p.m. on Wednesday. And then you can of course make an appointment with him too by sending an email to this address. All right. His office is also in the Crowd Hall. So, any question about this class overall? Nope. Can you dive into science now? All right, let's dive into science now. So, air pollution. I don't know why you guys have signed up this class. Anybody is brave enough to talk about why you signed up this class? What intrigued you to sign up this air pollution class other than all other science classes offered at UCI? No? You can say something. Okay?
It satisfies more than one GE.
What's that?
It satisfies more than one GE.
Oh, yeah? That's good reason. Any intellectual reason out there? Rather than, oh, it's not another offense, but any intellectually intriguing reason out there, rather than just require that the graduate requirement kind of thing. Yep.
Well, I lived in Los Angeles.
Okay.
And if you see any photo of smog or something, probably LA.
Okay.
So that's kind of why I was interested.
All right. Any other reasons? All right. I guess good enough. I guess so. When I take all those literature class when I was in college, I have the same reason that you have actually to just satisfy for the graduation actually. When I take the literature and then all sort of social science class also. So that can be actually a good reason. So I'm just kidding about it. So air pollutants we discussed about is all about matter, right? The stuff in the air. So when you just call it stuff, that's not really scientific term, right? The matter in the atmosphere, things like that. It's not a scientific way to describe air pollutants. So we will, for the first discussion of this class, we will talk about how air pollutants composed of. So most smallest unit that all the matter has in the atmosphere, all the stuff have in the world more than the atmosphere, is all composed by atoms. So every science classroom, if you just went to high school, then know this periodic table. So this is list of atoms in the world right now, at least we know of. So there's about more than 100 atoms out there. So atom is electronically balanced. So there's proton, which has small particle, has positive charge, and then electrons in the atom. And then atom has balance between number of protons and the number of electrons. So it's electronically balanced, right? But if it is not balanced, we call it ion. So it can be a positive ion and negative ion, depending on what's the balance between them. So if you have 2 protons and 1 electron, there's 1 excess protons out there, so it's positive ion. If it is 2 protons and 3 electrons, it has 1 excess electron, so it is negative ion, right? So atomic mass is so basically how heavy it is. So it is pretty much defined by number of protons and then number of neutrons. So atomic number is number of protons. So let's take a look at this periodic table. One here, one there. So out of this many atoms in the world, we will, in this class, we will probably discuss this. How many of this? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 atoms at most. And then we will discuss probably only 3 atoms, mostly during this discussion of this air pollution, all right? Which is hydrogen and carbon and nitrogen, oxygen, fluorine, chlorine, sulfur, mercury, and lead, all right? Probably mercury and lead, we are not going to talk that much, maybe an hour or so. But we'll talk a lot about hydrogen, carbon, nitrogen, and oxygen, all right? So, so there's a number there, which is atomic number. So this atomic number is indicate that how many protons this atom has, right? So hydrogen has 1 proton, carbon has 6, nitrogen has 7, 8, and 9. So the number up here is how many protons each atom has, right? Sulfur has 16 and chlorine has 17. So this number of protons pretty much defines the chemical and physical character of this atom, all right? This is the list of things. So this is atomic numbers right here. And then there's neutrons in there, which defines the mass of atom along with this proton. So hydrogen has just 1 proton. So mass of this hydrogen is 1. And then helium has 2 protons and 2 neutrons. The mass is about 4 right here. And then carbon has 6 neutron, 6 proton and 6 neutron. So the mass is about 12 gram per mole. So nitrogen has 7 and 7, oxygen and 8 and 8. But as I said, the character of the atom is determined by the proton. But the atom can have different number of neutrons. For example, carbon has 6 protons. So most of carbon in nature has 6 protons and 6 neutrons. But some of carbon has 7 neutrons. So the mass of this thing is going to be 6 plus 7 is close to 13. Then some of this carbon has 6 protons and 8 neutrons. So mass is going to be 14. So we call it carbon 13 and carbon 14. But because carbon 14 has too many neutrons in the system, you can understand this way. But it's not really scientific, but you can just understand this way. So too many neutrons in the system, so it is unstable. So it is decayed away from carbon 14 to nitrogen 14, and then half-life of this thing is about 6,000 years, which means that if you have 10 on carbon 14 right here, and then if you come back 6,000 years later, and then half of them is going to be changed to nitrogen 14. So this is definition of the isotope. So this is we call it this carbon isotope 13 and then carbon isotope 14. So this is conceptual figures of how atoms looks like, right? The hydrogen has 1 proton and 1 electron. Then proton is relatively heavy, so it is sitting in the middle of the atom, and then this electron is kind of moving on the around this proton. All right. So this is how helium looks like conceptually. Has 2 protons and then 2 neutrons, and then again, these are heavy, so it's sitting in the nuclear, and then these electrons are flying away on this proton and then neutron. So this is how atom looks like. And then if you somehow bring the atoms together, then you can make a molecule. So based on this, although this is only about the 100 atoms or so we found in the nature, but you can make 100 millions molecules out of it, because how depends on how you can just make putting atoms together. So you can usually think that this is the kind of Lego blocks for the geeks, all right? So so there's a neutral, the electrically neutral group of 2 or more atoms, kind of bonded together. We call it the molecule. So we call it chemical bonds. Is that okay? So for example, the water, right? So oxygen, as I said, has 6 electrons, and then hydrogen has 1 atom, 1 electron. So somehow nature, this world of atoms, loves to have 8 electrons in the system. So actually, oxygen has 8 electrons, but outside of the shell, there's 6 electrons in there. So how can you make how can we satisfy 8 electrons by putting this thing and this thing together? It's one way to do it, is that oxygen can share 1 atom with the hydrogen, right? And then the other electron with the hydrogen. So oxygen now can have 8 electrons. So this is how you can build the stable molecule. So that's why we call it water as H2O. So this is one way to, so usually most common way to write the molecules, how the molecule composed by the atoms. So let's just quickly test our iClicker thingy. So there's a list of thing of the equation there, if you will. So which of these things are molecule, or all of the above? There's 5 choices there.
It's not working.
It's not working? Ah. That's why we need to test it. So this is not going. Yeah, probably today everybody's attended. So I will, is that worked? No? It's not working? You want to try again? I will try. Yeah, this. So this green thing is the number of responses, right? So I'm getting responses.
I press CC.
You guys press CC?
Yeah.
Ah.
I press CC like before. It didn't work.
Ah.
Before you press CC, you have to press and hold the other button.
Oh, hold it?
Yeah.
Oh, that's my fault.
Do I hold it and press CC at the same time?
No,
So
just flash.
hold the on,
Yeah,
and then make this thing flash, and then push the CC.
Okay, thank you. Appreciate that. Got it.
ta-da.
All right?
Sir.
Sure.
Clearly, I'm gonna sound okay.
So everybody try that? I guess there's more than 34 in this classroom. So let me know if you didn't bring the iClicker today. Yeah, let's test it. So C is the most dominant answer. So the answer is actually all of the above. So oxygen is molecule, okay? So as just exactly same reason, water is molecule, oxygen is a molecule, because let's think about this thing again. The outer shell of oxygen, there's 6 electrons. So this, if you take a look at this periodic table, there's a small number thing there. So this 2 means that this has each shell. So this is shell 1, shell 2, shell 3. So shell 1 can contain the 2 electrons. And then shell 1 can contain 2 electrons, and shell 2 contain the 8 electrons right here. But oxygen is right here. So in the shell 2, lithium has 1 electron. This thing has 2 electrons, 3 and 4, 5 and 6. So oxygen has 6 electrons outside. So how can we make this oxygen atom happy to share electron with another oxygen atom to make 8 electrons? Then they can share 2 electrons each other, right? So this is how you can build the molecule. So if we can make 2 oxygen atoms to share their 2 electrons, then it's gonna look like this, right? Then this oxygen atom has 8 electrons, and then this oxygen atom also can have 8 electrons. So both atoms get happy, all right? So the chemical bonding means that if they share their 1 electron each, we call it chemical bonding. So this thing share their basically they just 1 atom provide 1 electron, 2 electrons each. So it is making 2 bonding. So we call it oxygen as O2, right? Probably most of you knows about this. So now you can say that there's 2 bonding between oxygen atom. So in terms of bonding structure, it just looks like this, okay? Just 1 stick right there means that bonding. So these 2 atoms share their 4 electrons, 2 electrons each from each atom, then making their 2 bonding, all right? So let's take a look at some other example. Hydrogen. So hydrogen, so it's right here, right? So right here it has 1 electron, and then the outer shell, it can contain 2 electrons. So it is kind of inner shell, so it can contain only 2 electrons. So it will be happy. Hydrogen will be happy if it has 2 electrons in the system. So you have 2 hydrogen there, 1 electron each. Then if they somehow share these electrons together, like this, then both of them will be happy, right? So this is one happy molecule called hydrogen, molecular hydrogen. And then in terms of chemical way, you can notate like this, all right? So this is how you build molecules out of atom. So there's a little interesting question out here. So we will talk a lot of ozone. So one student mentioned about LA has a pretty big smog problem. One of the important molecules that we are dealing with in terms of air pollution in Los Angeles is ozone. So ozone has 3 atoms, and then this thing is also a molecule. So this oxygen already, 2 oxygen atoms already happy by sharing the 2 electrons each, making this 8 electrons kind of share by sharing the 2 electrons. Each atom can have the 8 electrons, right? So if you have another oxygen atom here, which has 6 electrons outer shell, then how you can putting this thing out here, make the 8 electron for each atom, is that there's 2 empty spot right here. So if you can bring this thing right here, then bring this thing like this way, then this atom also has 8 electrons, right? So this thing has 8, so this thing has 8. So everybody has 8 electrons, right? So this is not as happy as oxygen in terms of stability, but still is stable enough stuff that we can call it molecule. So basically this is notation of the you can present molecules in scientific way, right? So that's the introduction about molecules. So another definition, so gas, particle, and aerosol. So gas is just like oxygen and nitrogen, something flying over in the atmosphere, right? And then there's some interesting distinction between particle and aerosol. So particle is basically, there's no chalkboard system usually has a good example of a lot of particle. So you can have a dust, things like that, you know. We call it just that thing as a particle, right? Even this thing can be a particle. So also, if you have any spray things like that, that liquid molecules just kind of aggregate of the molecules in the atom in forms of the solid or liquid phase, we all call it particle. So raindrop is particle. That's a good example. So once raindrop is in the atmosphere, in the air, once it is flying in the atmosphere, then we call it aerosol. But if it is, dropped down to the ground, from that time we call it particle. All right? There's a difference between particle and aerosol. So everybody is getting the difference between particle and aerosol. So once that whatever size of the material is flying over the air, we call it aerosol. And then particle is more broad term that regardless it's in the air or on the ground, we call it just particle, all right? So there are 3 states of matter we will discuss during this class. One is solid and liquid and gas. So one of the easy way you can define the solid, liquid, and gas is that solid holds a shape by itself, just like ice cube, right? Ice cube holds its shape, regardless the container shape, it just holds a shape, right? And then it has fixed volume. And then liquid, so once ice melts, it becomes water, right? Liquid water. So liquid changes shape, depends on the container. And then volume is fixed, relative, in precise way, actually liquid volume is changing. But in general, liquid volume is fixed. But one of the important difference between liquid and gas, it will change the its shape, depends on the container. But the volume of this thing is not fixed. It's more like changing, depends on the container. All right. So this is a nice way to present the difference between liquid, solid, and gas in non-scientific way. But we scientists usually talking a lot about this state related with the energy. Actually, I told you that we'll discuss about only 3 different states of matter during this class, which is gas, liquid, and solid. But there's another actually state out there called it plasma, but we'll not discuss about this thing during this class. So in terms of energy, gas has highest energy. So let's think about the ice cube, right? So ice cube, if you just heat it up, it becomes water, liquid water, right? If you just boil things out, then it will melt and then becomes the liquid, right? So because it takes the energy from the outside. So if you boil more and more and more, then it will become water vapor. Then it will be evaporated to the atmosphere. Then it becomes the gas. So that's how you define the states of matter. And then there's a number of different ways. If gas becomes solid, we call it deposition, and then all those fancy words out here. At this time point, you don't need to worry about that, the phase change. But in terms of the define the solid, liquid, and gas, you can define the relatively easy way, the relatively difficult scientific way out there, defining state of energy by states of matter by the energy differences. Okay, And then you can remind yourself the states are defined by their energy, by the ice cube example, that if you just heat it up, that ice cube, it becomes the liquid and then gas eventually, right? So that's it. So definition of air pollution. So we actually need to define the air pollution. It can be many different phenomenon out there. So there's all different issues out there that it can be expressed many different ways. But there should be one consistent definition of air pollution to define what's the air pollution, what's not air pollution, things like that. So, the one way to define the air pollution is that it can be, the air pollutants can be both gas and particle in the atmosphere, which by definition aerosol, right? As already I told you. And then, but it should be anthropogenically emitted. So anthropogenically emitted, so anthropogenic means that human source, okay? So basically human, by the human activity, there's excess amount of gases and aerosol particle in the atmosphere, and then the concentration of those things is built enough and then high enough that can damage human health, whatever, or plants, or animals, any other life forms, or ecosystem, or even structures, man-made structures, and then works of art. So this is the one example of the acid rain. We don't talk about acid rain that much in this country because we addressed quite a bit about the acid rain phenomenon in this country that we will discuss later part of the discourse. So when the acid rain is, acid precipitation is coming, because of the acidity of the water, that the leaves of the this tree actually turn white. So basically, the leaves are dying, right? So this is definitely air pollution because so acid rain is caused by man-made, human-made gas, and then that caused the acid rain, and then the trees are dying. So this is definitely air pollution problem. Also, the acid rain, because it is acid, all those kind of historical statue kept outside is kind of melt away. If you take a look at this, you can identify the face there, but due to the acid rain, it just all melt away. So this is a good example of the acid rain, how we define acid rain as air pollution. All right, so let's do a little example here. So yeah, this is new slide actually I put in for this class. So we call it Anthropocene as a modern time. So so previous slide I talked about anthropogenic. So anthropogenic is a kind of a word combined together. Anthro means human. Pogenic is origin, right? So human origin pollutants, right? And then Anthropocene is the human period. So if you take a look at this video a bit, then you will understand about this Anthropocene relatively well. Let me play this thing.
This is the story of how one species changed a planet. The latest chapter of our story begins in England 250 years ago. Fueled by coal, then oil, several brilliant inventions appeared. They ignited the Industrial Revolution, which spread like wildfire through Europe, North America, Japan, then elsewhere. The great railways, then cars and highways, connected people across the globe. Medical discoveries saved millions of lives. New artificial fertilizers meant we could feed more people. Population rose rapidly. But this was nothing compared with what was to come. The 1950s marked the beginning of the Great Acceleration. Globalization, marketing, tourism, and huge investments helped fuel enormous growth. People swarmed to cities, which became even more powerful engines of creativity. In a single lifetime, the well-being of millions has improved beyond measure. Health, wealth, security, longevity, never have so many had so much, yet 1 billion are malnourished. In a single lifetime, we have grown into a phenomenal global force. We move more sediment and rock annually than all natural processes, such as erosion and rivers. We manage 3/4 of all land outside the ice sheets. Greenhouse gas levels this high have not been seen for over 1 million years. Temperatures are increasing. We have made a hole in the ozone layer. We are losing biodiversity. Many of the world's deltas are sinking due to damming, mining, and other causes. Sea level is rising. Ocean acidification is a real threat. We are altering Earth's natural cycles. We have entered the Anthropocene, a new geological epoch dominated by humanity. This relentless pressure on our planet risks unprecedented destabilization. But our creativity, energy, and industry offer hope. We have shaped our past. We are shaping our present. We can shape our future. You and I are part of this story. We are the first generation to realize this new responsibility. As the population grows to 9 billion, we must find a safe operating space for humanity, for the sake of future generations. Welcome to the Anthropocene.
So I'm playing this video not because get you freaked out, but kind of a story about the air pollution is kind of branch of this whole kind of environmental change that caused by human, right? So we'll specifically talk about the atmospheric part of local air pollution. Just like a student said that Los Angeles is a big problem. You may think that that's just regional or local issues, right? But what we have realized is that those kind of regional and local issues caused by human are actually kind of spread out to the world, and then we are changing. Obviously, there's many indications coming from the Earth is that we are changing whole environmental system of the Earth. So we will discuss about very small regional scale of the air pollution, and then in the end we will talk about the global scale air pollution also towards the end of the quarter. All right. So this is the kind of overview of this class. So this class is not over yet, and there's another iClicker question. So based on that definition of that air pollution, where is the little thingy? It's here. Okay. So which one of these things is not caused by air pollution? So this thing, actually I got this thing from the internet somewhere. This is Atlanta, where I went to grad school in late 2000. And this is, I took actually photo of this thing in China. As you can see, very hazy. This is another photo somewhere from the internet. Dust storm from the desert over the car. And then this is another city, actually my home, Seoul, South Korea. As you can see, the haze stopped there. So which of these things are actually not air pollution, or all of the above? I think I can wait 15 seconds. I think there's more than 34 students, 36, all right. Okay, I guess no more responses. I will stop this thing. Let's see this. Okay, there's a D and E. So a little more students actually voted for the E, and then a little less than D, but somewhere between D and E. There's A and C. Let me hear about a student's opinion who choose E. Maybe D. Why somebody choose D? Any reason?
Dust storms naturally happen.
That's right. So the answer is D. So dust storm is actually naturally happens. So this is not really air pollution, right? So anything that happens naturally is not air pollution. So in this case, dust storm is not air pollution, right? So he got it right. But obviously, there's some issue that there's expansion of the desert out there in Africa and China cause more often, just making this dust storm phenomenon more often. And then that can be, you can call it air pollution or not. It's a little gray area, but this is a natural phenomenon, so we don't call it, unless during this class, we are not gonna call this thing as air pollution, all right? So we talked about before about solid, liquid, and gas, 3 states of matter. So air pollutants can be, solid, gas, and liquid too. So I will just give you one example each for the liquid, solid, and then gas. One example of a solid is lead. So we don't call it as lead, we call it lead. So we found this thing as a human kind about 6400 BC, which means that about 8400 years ago, quite a long time ago, right? So this is how lead ore looks like. And then I don't know how many of you actually touch the lead, but lead is very malleable, which is very, you can play with it and then make a shape very easily. So past Roman Empire, people built water duct system using this lead pipe. So people actually drinking water from this lead pipe. So if you travel Rome, and then you can still you can find this kind of the water pipe system in the Rome from the Roman Empire. But the problem of lead is that it can affect on your health, like kidney, and then basically you can get very dumber to take too much of lead. So the problem of the Roman Empire is one of the theory. Actually, I think that's not really historically true. But some people claim that most of people that's kind of a politically high people drink the water from this lead pipe. So they just took too much of lead. Just they are getting dumber and dumber, and then that's why the Roman Empire is gone. There's some people actually just joked about that thing. I think, but there's a little truth on it. But this is I shouldn't talk about this thing because it is recorded. But but that's one I just heard that once people just joked about it. So that's actually, but it is true that there's a lot of health problem actually caused by this lead water pipe system. If you read the textbook, there's some more description about it. But the story is not stopped there. Actually, we have added lead to our gasoline till mid-70 or early 80, I think, if I remember correctly, in this country, in the US. Then other country added lead a lot to their fuel for the anti-knocking agent. So that caused a lot of problems. So we will discuss about this thing, I think next week, next Thursday, the lead added gasoline. But these days, nobody added lead on their gas. So if you just find the old gas pump, there's you can clearly see there's leaded. So which means that they added lead on the gas from 40 to mid-70 in this country, later to other countries. So that's one example of the solid as an air pollutant. The other example is liquid. So this is one of the geologically very active area, Indonesia. And then this yellow stuff is sulfur. So sulfur was kind of found about quite a long time ago, about 4000 BC, probably in terms of history. Old Testament write about the Sodom and Gomorrah, and then one city is destroyed by the volcano. So this sulfur there's a lot of sulfur below the surface. So when there's a volcanic eruption, so a lot of sulfur is coming out to the atmosphere. Once sulfur is getting out to the atmosphere, it becomes SO2, and then it becomes eventually sulfuric acid, which is liquid. So as I told you that the lead as a solid thing was found like 6400 BC, quite a long time ago. But people realized the existence of this sulfuric acid, which is a liquid, about 1500, right? So it's quite, compared with the realization of the solid as a pollutant, is pretty recent thing. So that's why you cannot actually see the molecule in the water, sulfuric acid, by eye, right? So you can clearly see the solid by your eye, but you cannot see what kind of molecule in the water in your eye. So that's why it takes so long time to realize sulfuric acid in the water. So sulfuric acid in the atmosphere eventually kind of a partition into the rain, and then once it rains, it becomes acid rain. So all the acid rain problem is coming from sulfuric acid, and then that's another example of the air pollutants as a liquid, all right? And then gas. So we will talk a lot about gas as all air pollutants during this class. So, and then one of the good example is ozone. So I told you about this ozone molecule out here. So ozone is molecule because 3 oxygen atoms share the A electron each, and then it's relatively happy molecules. And then it was found late 1700, actually late 1800 by the Schoenbein, who is a chemist from Germany. So how many of you heard about ozone? What's your name?
Romana.
Can you tell me about what do you know about ozone?
Ozone blocks UV rays. Right?
Okay.
Yeah.
Anybody knows any other story about ozone? So that's all you know about ozone? There's
a hole in Australia, right?
more like Antarctica, a little more south.
I thought there was one above Australia because of all the sheep.
Really?
Yeah.
I mean, I think we need to talk about it.
Apparently there's like a chemical in the wool, and it breaks down the ozone there.
Interesting. All right, let's discuss about that thing as time progress. So anybody knows any other story about ozone back there?
Doesn't it cause pollution when it's like near humans and stuff like lower in the atmosphere?
So now you heard that 2 story about ozone. So when ozone exists in the stratosphere, which is about 20 kilometers above us, it can protect us from UV. What's your name again? Romana. As Romana said, that because it absorbs UV, and then UV, which is very harmful for human and other animals, that's why we put the sunscreens on it. So it is observing UV, not to getting into to the ground. So this is good ozone up there. But if that ozone somehow exists in the ground, if we breathe it, it is very bad molecule, all right? So stay up there is a very nice molecule. If stay on the ground, air that we breathe is bad, all right? There's 2 different ozone out there. So don't confuse about it. I heard a lot of confusing story about. I think the ship thing is one of the other story. Let's talk about it. I'm not gonna show that. Yeah. All right. So this is an example of the gas as air pollutant. So this is also gas, but if you just read the whole textbook about the history, about the finding of the molecule, solid, liquid, or gas, whatever, it's all about scientists, male scientists, right? And then if you get into the Marie Curie section, you finally found one female scientist. So she also won 2 Nobel Prize. So she's a very outstanding scientist. And then her contribution to scientific community is finding of radioactivity. So I briefly talked about isotope. Isotope can be unstable, and then it can be decomposed into other atoms. So when it decomposes or decay, it can emit very energetically high particle, alpha particle or beta particle. So this is what we call radioactivity. So for example, X-ray, things like that, that's the highly energetic particle, all right? So why this thing can be air pollutants? So a couple of years ago, there was a big problem of the nuclear power plant in Japan, destroyed by tsunami, and then it emits a lot of the radioactive material to the atmosphere, and then that kind of freaked out the whole country of the Japan and the whole Asia, and then even some news article in California worried about the transport of this thing into the US. So because this is man-made problem, right? So this nuclear power plant is man-made, somehow leaked out some radioactive stuff to the atmosphere that can affect on your health, my health. So we call it air pollution, right? So one of the examples, if you take a look at, so this is one of the model results, how fast the air can move from Japan to the US. So it takes some time. Let's take a look. Let's go. We need a better computer in this classroom. It's really slow. Okay, I guess until we wait, we can talk about some other stuff. So I'm not going to play this thing. I think I also put the link for this news article from CNN. So this news article is about, if you take a look at the video out of it, so about the fish is contaminated by the radioactive stuff in the water. Obviously, there's water also leaked out from the plants, and then it contaminating all those water near there. So people kind of got freaked out eating fish. So that's a little tiny little article about the danger of eating fish because of this accident in the local newspaper in California. But in California, it's not a big deal. It's too far away from the Japan. But in Asian country, for example, I visited Korea actually 2 weeks ago. Then a lot of people don't want to take any fish because it is kind of contaminated by this thing. So another way to contaminate the water instead of the air by the power plant is still going. So maybe we should wait until the end of the class. So we looked through the history of the finding of the air pollutants, gas, solid, and then liquid, and then even radioactive stuff, right? Fine. Oh. Let's go down. Let's check. Still going. So there is, yep. So you don't need to know about all this molecule, but this is kind of introduction, that what kind of molecule I will talk about this during this whole quarter. Mostly, so sometimes I will talk about oxygen and nitrogen, but oxygen and nitrogen are very stable molecules in the atmosphere. They are not really reacting with anything. So this is basic matrix of air. So about 99% of air is composed by the oxygen and nitrogen. So I will talk a lot about ozone, SO2, which is precursor for acid rain, which is sulfuric acid. So I will talk a little bit about SO2. I will talk about CO, little bit of this hydroxyl radical thing, and methane, NO, and NO2. Probably about, and CO2, of course. And about 10 molecules also. So if you remember about 10 names, you are pretty much safe for the hold this class. And then this thing maybe get you freaked out. So this is kind of difference between inorganic molecule and organic molecule. If you take a look at this molecule, list of a molecule, they are all composed by oxygen or nitrogen, right, or sulfur. But if you take a look at this, so this is what we call organic compounds. So when you hear organic, probably non-scientific people, organic is some, you probably mind yourself Trader's Joe or, or Whole Foods, things like that. But for the scientists, that's not organic. Organic compounds is the molecules composed by carbon. So that's organic molecules. So we will talk about a little bit of the organic molecules. So you don't need to remember all those names. So when you hear the organic molecule, so by definition, organic molecule is a molecule kind of built by the carbon backbone. Okay, that's the by definition organic molecule. So so those kind of molecule in the atmosphere is not staying as it is, but they are reacting each other. So that's how make this story much more complicated. So we will talk about the reaction is happening in the atmosphere. So there are a couple of examples of the reactions right here. So at this time point, you don't need to worry about what kind of reaction is what. So what you need to understand from this class is that people emit some gas or particle, things like to the atmosphere, then they are not staying in the atmosphere. Also, they are reacting each other, making another air pollutants. Okay, that's the whole story about behind of this thing. And then we will talk about this lifetime a little later, but we will talk about unit a little bit for the last topic. So there's some difference between math and science. So math is just playing with numbers, but science, we always respect unit. All right, this is one example. So country of Zimbabwe, so somehow their currency is so inflated, so they need to print it out $50 trillion bill or $100 trillion bill. So if you are not really know about the unit, if you just hear they're $100 trillion, well, that sounds a lot of money. But if you convert that thing into US dollar, on the eBay today, you can buy this $100 trillion bill as with $3. That's one bid, $2.95. Probably you can just bid this bid very easily if you just bid $5, right? So you can get the $100 trillion bill very easily with the $5. So this is kind of a example why the unit is very important, right? So it's different unit, right? Zimbabwe dollars and then US dollar is two different things. So when you talk about something, some numbers in science, you really need to notate what's the unit of it, all right? But the problem of teaching science in the US is the US is the only country not observing science units, okay? All the other countries in the world using the scientific unit. So for example, if you see this sign out there in Canada, maximum speed is 100 is kilometer per hour, right? So which is 1.6 miles, which is about 65 miles per hour, okay? So don't just shoot it out, all right? So we will use scientific units for this class, which is kilogram as a weight. So you are using a lot of time pounds, so 2 pounds is about 1 kilogram. As I said, I will use a meter or kilometer during the whole this class. I'm not gonna use the miles at all. And then this is this. And then most of you guys confused by Celsius. So Celsius, and then I will either use Celsius or Kelvin. And then there's a little equation there. So we will discuss about this thing next time. But last but not least, let's take a look whether this thing is still running. Okay, I will exhibit this thing out next time. All right.